So let us see on how we can be able to find the electric field of a point charge. How can we be able to find the electric field of a point charge? So last time we looked at the analysis of the electric field and also electrostatic force. So make sure before you go for this, you have to go through that video, because it is a part of the concept continuation. So you should know that. Let's say we have a point charge. This is given as the point charge, and that is given as the negative charge. Actually, it should be a positive charge. And we have a test charge here, and also given as the positive charge. And let's say the charges are separated with some distance given as r. That is the separation distance. And now, in this case, what is the force in which a test charge experiences due to actually this particular point charge? And we know that it is given as electrostatic force given as Fe. And this region is said to be the region of electric field, and of which the electric field, we discussed that the electric field is given as, that is Fe, that is the force, divided by, that is the test charge. This is how the electric field can be calculated, the field graded within this region due to the electrostatic force. And let's say we should have to analyze further about this actually context. Of course, this is the electrostatic force. This charge you're going to experience, and this is due to this charge as well. But using the Coulomb's law, what is this electrostatic force? We'll have it as Fe being given as, K times, a point charge, and it times the test charge divided by the separation distance square. And let's think of substituting this one into here. Now we'll have it as electric field, and being given as now K times the test charge times the point charge divided by r square, and it times 1 over the test charge, of which this and this one will cancel. We'll have electric field that will be given as K times the charge divided by, that is r square. So this is how we find the electric field due to the point charge. So if we know whichever the point charge, and we would like to find the electric field at whichever the point, so this is the formula that we use to find the electric field due to the point charge. That is, let's say if we have a point charge here, let's say given as a positive charge, and we'd like to find the magnetic field, let's say due to this charge at, let's say, this point P, and this is the separation distance between the two. Let's say this is the separation distance. So the magnetic field here due to this charge will be given as the electric field at this point due to that charge will be given as, K absolute value of a charge divided by the separation distance square. That's how it will be. And that is for whichever the case. So what do you think is the direction of the magnetic field at this point? So using the same analog, if this is a positive charge, magnetic field lifts the positive charge and going outwards. It means let's say this is the line of action. At this point, magnetic field will go towards this direction. So which means the direction of the magnetic field at this point will be towards this positive direction. That will be the direction of the magnetic field. And what if this was a negative charge? What did you say? Let's say if this was the negative charge. Let's say we have it as a negative charge. Now, since this is the negative charge, magnetic field enters the charge. Magnetic field enters the charge. And let's say this is the line of action. It means at this point, the magnetic field could have entered the charge. So which means it could be towards this direction. So always the direction has to be emanated from the point of interest. So which means this is the direction of the magnetic field. If the point charge, I should say if the point charge is a negative charge. So you should have to bear this in mind. If the point charge is a negative charge, magnetic field lines enter the charge from the infinity. So which means whichever the point, the magnetic field region, actually a magnetic field lines should have to move from the actual point towards this. And if it is a positive charge, it means the magnetic field has to leave the charge towards the infinity. So keep that in mind about that. So you should have to understand that whenever we are calculating the electric field due to a point charge, you know the charge has to be given as the absolute value. So the charge has to be given as the absolute value. So that's how we make it up in that case. Now let's see about the superposition principle in one dimension as well as the two dimension. So it is the same way we discussed about the superposition principle for electrostatic force. You know, nothing different. It is the same way you talk of the analysis, you talk of looking at the directions, vector resolutions concept, and sort of. Let's say we have the system of the charges in, let's say, one dimension. This is charge 1, a positive charge. And let's say this is charge 2, negative charge. And let's say this is charge 3. Let's say given as the positive charge. This is also positive charge. Now, what is the net electric field? Let's say, what is the net electric field on a point charge, let's say a Q? What is the net electric field on a point charge Q2? We're looking for the net electric field E2 net, meaning the net electric field should be the net electric field. So what is the net electric field at a point charge given as Q2? What is the net electric field at a point charge, actually at a point charge Q2? So now we call it as E2 net, that is the net electric field at a point charge Q1. So since our point of interest is at the point where there is a Q1, it means, I should say, since our point of interest it is on the point where there is a charge Q2, it means a charge Q2 will have no contribution towards the electric field at that particular point. So in this case we'll have the electric field due to charge 1 and the electric field due to charge 3. We'll have it as that. So let's see if the actual fields will be negatives or positives, and therefore a charge. You know, this is the positive charge, and of which always electric field lines moves from the charge. So if this is the line of action, it means at this point electric field will go towards this direction. So hence that won't be positive. And on the same case, this is a positive charge, of which the electric field lines lifts the positive charge and towards the infinity. If this is the line of action, then at this point electric field will go towards this direction. Hence we'll have negative here. And let's say the distances is given as A here and given as B here. What will be the value of E1? So E1 will be given as K charge 2 divided by A square. And what will be the E3? E3 will be given as a K charge 3 divided by B square. That's how it will be. Then we'll substitute and be able to have what is the net electric field at that particular point in that case. So it can be negative or positive. If it is negative, it means the direction it has to be, it means the net direction has to be towards the negative direction. If it's positive, it means towards the positive. Now how about, let's say, the net electric field at some point? Let's say this is a point Q. What would be the net electric field at a point Q if that's the case? So principle remains the same. Now since this is a point where there is no charge, it means each charge in the system will contribute the electric field at a point Q. And let's say this is a distance, this is A, this is B, and this is C. So have electric field due to charge 1, charge 2, and also charge 3. Let's see the signs of let's see the directions of the electric fields, and for that point Q. What is E1? So E1 will be towards this direction, will be positive, hence we'll have it in that way. How about E2? E2 will be towards this direction, will be negative, so have negative. How about E3? E3 will be towards this direction, also be given as the negative as well. So this is the expression for net electric field and at a point Q due to the other charges. How about, let's say, the net electric field at, let's say, this point. Let's say this is a point B. Let's say this is the point B, and it is at some, let's say, it is at some distance C. It is at some distance C from, let's say, a charge 1. What did you say? The net electric field at a point B will be given as, electric field due to charge 1, electric field due to charge 2, and also charge 3. So can you come up with expressions based on the directions there, either positives or negatives? And also appreciate this one as well and see how we can have it okay. Let's say this is the system of the charges. We have here charge 1, here we have charge 2, we have here charge 3, here charge 4, and here charge 5. Let's say the distances are given as A, B, C, D. Let's say that is. And this is the negative charge, negative, positive, negative, negative. So can you come up with the expressions? Can you come up with expressions on the net electric field at a point charge 1, the net electric field At a point charge 2, I should have this. What's happening? I should have this. So come up with the net electric field at a point charge 1, the net electric field at a point charge 2. I need the expressions there. The net electric field at a point charge 3, and the net electric field at a point charge 4, and also the net electric field at a point charge 5. Can you come up with those expressions? And I also come up with the expressions for the net electric fields. Let's say at this point, let's say this is a point P, let's say this is a point Q, let's say this is the point S, and let's say this is a point M. So come up with the expressions and for the net electric fields in those corresponding points. Now let's say we have this typical problem, and appreciate how we can have it. Let's say we have the system. Let me use another ink here. We have the system of charges. Let's say this is charge 1, negative, is given as 2 coulomb. And let's say this is charge 2, given as 5 coulomb. And let's say this is charge 3, given as 1.5 coulomb. We have that, 1.5 coulomb. Let's say this is charge 4, given as 2 coulomb. And let's say the aspiration distances given as this is 2 meters, 2 meters, 1.5 meters. I'll have that. And assuming that we have a point, that is the point which is at the midpoint between Q1 as well as the Q2, given as a point Q. Now what is the net electric field at a point Q due to the charges in the system? So in this case we'll have the electric field due to charge 1, and due to charge 2, due to charge 3, and also due to charge 4 as well. That will be that. Now let's see the directions of these actually electric fields at that point Q. So E1 will be towards the left. We'll have it as a negative. How about E2? Well, let me have this one as, this is a negative charge, positive, negative. We'll have that. And how about E2? E2 will also be towards the positive direction, because it will be towards this direction. And how about E3? E3 will be actually towards the negative direction. And how about E4? I understand how these directions have been given. We are looking at the charge, whether it is positive or negative, and we're looking at whether the field lines has to leave the charge or enter the charge, and with respect to the line of action. And how about E4? Now E4 will be the positive. We'll have that. And using the formula for the electric field due to a point charge, we'll have to calculate what is E1. What is E1? So E1 will be given as 8.99 times 10 to the power 9, and then times the charge. What is the charge? Q1, that is given 2, divided by the separation distance, and which is, since this is the midpoint, then it means Q1 is of a distance 1 square. So we'll calculate what is that. And E2 as well, it is at some distance 1 meter, and E3 it is at some distance 3, and E4 it is at some distance 1.5, 4 plus that one. So proceed with the other calculations and appreciate that. In their own time, also try to find the net electric field, let's say at this point. Let's say this is point A, and also at the point A. And appreciate, assuming that these are the midpoints between this and this, this and this as well. So that's how you should have to understand about the superposition principle of the electric field in one dimension. So let's finish with superposition principle in two dimensions for the electric field. Let's say we have, this is x-axis. Let's say we have, this is x-axis, and let's say this is y-axis. Now we have, this is, let's say this is a charge 1 giving us the positive charge, and let's say this is a charge 2 giving us the negative charge. I should say positive charge as well. This is a positive charge and that is a positive charge as well. And let's say this is a charge 3 as a negative charge, and let's say this is charge 4 as a positive charge. We have charge 5 as a negative charge as well. So what is the net electric, let's say, what is the net electric field at this point? Let's say this is the point Q due to the charges. So principle remains the same, like the way we discussed about the superposition principle for electrostatic force in two dimensions. So this is a point which is at a position where there is no charge. It means all these charges will contribute the electric field at that particular point. So that is to say, E net, EQ net will be given as E1. Now in this case, since we are in two dimensions, the expression for the E net will just be literally add. So E1 plus E2 and a plus E3 and a plus, let's say, E4 and also plus E5. We just have to retry add. Then we're going to find these electric fields using the formula for the electric field due to a point charge, and by also looking at their respective distances as well. And wherever there's need of solving the distance, you'll be required to. For example, distance between the point and the charge 1 is given as this. So there's need of using Pythagoras theorem in case we have those distances. And also between these, you can also be required to do so. That is, then you calculate in the afterwards, you should be able to resolve these electric fields into components and do the same way we discussed about the electrostatic force superposition in two dimensions. So for instance, E1, what is the direction? Mind you, the direction has to be from the point, from the set point. So E1 will be towards this direction. Therefore, we'll have to resolve E1 into components. We'll have, this is X component and this is the Y component. And this is the angle of interest that I'm going to use to resolve that into components, of which always there has to be a way of making it up. You should know that first thing you connect the two. That is, and E1 has to be resolved into components. This is the X component and this is the Y component. So this angle is the same as this angle, of which this angle will be calculated using the trigonometric ratios. So this is the X component towards the positive direction, and this is the Y component towards the negative direction. You do that. And let's go for E2. E2 We are saying it is towards this direction. So we'll resolve it with two components. That is x component as the negative, actually as well as the y component, of which x component will be the same as this, only that it will be a negative. And likewise, you also go for E3 as well. So E3, it will be towards this direction, since this is the negative charge. So since it is towards this direction, then this is A3. You resolve into components. X component as well as the y component. Then from there, you see that since this electric field is in the horizontal axis, then x component will be the same as this, but it will be negative. The y component will be zero because it has no y component in that way. You indicate that one. Then E4 principle remains the same. E4 will be away, will be towards that direction. That is E4. Mind you, the electric field has to be emanated from the, whenever we are looking at the direction, whenever we are resolving whatever we are talking about, we are dealing with, should be based from the point of interest. So you can see that E4 is in horizontal axis towards the positive direction. You also resolve that one, you have x component as well as the y component, of which y component will be given as cell. X component will be the same as that one. And how about E5? It means we have this. That will be E5. That will be the connection between the two points. So what will be the direction? This is the negative, will go towards this direction. Then you'll be able to resolve that into components in that way, of which this angle will be the one used to resolve. This is x component towards this direction, this is the y component down. So both will be negatives. Then you add all x components and y components and find the magnitude as well as the direction of the electric field at a point Q in that way. Now try to solve this at your own time with some friends or yourself if you can. Let's say this is the system. We have two-dimension coordinate system. And this is a charge 1, negative charge, that is given as negative 2.7 nanocoulomb. And this is a charge 2, a positive charge, that is 4.2 nanocoulomb. And let's say the distance is given as 5 meters. This is 4 meters. We have the charge at the origin given as negative charge, that is 1.2 nanocoulomb. Then we have, let's say, a charge, this should be charge 3. We have charge 4, that is 9.7 nanocoulomb. Let's say this is about 2 meters. Now here's the question. Find the net electric field at the point charge, which is at the origin. Find the electric field at Q3, B on Q3. Find the net electric field at Q3 on Q3. So I want to see the differences between the two actually prepositions from you viewers. Thank you, and don't forget to subscribe to the channel, as you'll be every time updated for whatever the content has been created the best for you. Thank you.